Hi everyone, I hope you're doing well. In this video, we're going to go over the geometry of alkenes. So their shapes, the angles between bonds, etc. But first, let's just review from the last chapter. Remember when we talked about the geometry of alkanes, we said that carbon has 4 valence electrons, but if we draw the orbital diagram, we see that only 2 of the electrons are unpaired and could potentially go on to form bonds. But we know that that's not true. We know carbon can make 4 bonds with 4 other atoms. So Linus Pauling came up with a way to get around this fact, and he said, okay, what if we combine our highest energy orbitals? So our 2s orbital and our 3 2p orbitals, and we make those into 4 hybrid orbitals. That way, each electron gets its own orbital, called an sp3 hybrid orbital, and those can go on to make bonds with 4 other atoms. And, this is a theory, but it works for what we're trying to accomplish or talk about here. So again, these sp3 orbitals, the name comes from the fact that we're using 1 s orbital and 3 p orbitals to make these 4 hybrid orbitals. And down below, we have an example shown here of methane, CH4, and that carbon atom in the middle is bonded to 4 other hydrogen atoms. And the hybrid orbitals want to spread out as far as possible. So we end up with a tetrahedral geometry. And the angles between all of those bonds is 109.5 degrees. So that's the ideal bond angle. Okay, what about alkenes? So for alkenes, we're going to actually form what are called sp2 hybrid orbitals to explain the geometry. So instead of combining all of the highest energy orbitals for carbon, we're just going to combine the 2s and then only 2 of the 2p orbitals. And that's going to create 3 hybrid orbitals called sp2 orbitals. So we're combining 1s and 2p orbitals, so sp2. Now that's going to leave one of our 2p orbitals unhybridized. So it's still just hanging out, doing its own thing. But we're still going to take our 4 highest energy electrons for carbon and place 1 in each of these higher energy orbitals. So we get 1 electron in each of the hybrid orbitals, and the last electron goes up into the 2p unhybridized orbital. Now this might seem really confusing, like why even do this, but it makes sense when we start getting into bonding and how double bonds form. Okay, so let's kind of look at what these look like here. Okay, so we said that during hybridization for alkenes, 2 of the 2p orbitals will mix with our single 2s orbital, and we end up with 3 sp2 hybrid orbitals. That's going to leave 1 2p orbital unhybridized. So down below, let's pretend that this is a carbon atom, and the nucleus is right in the middle here. So we said that we have 3 sp2 hybrid orbitals that have formed. So those are going to be in the middle, kind of in a circle around the center. And remember that electron groups like to be as far away from each other as possible. So if you imagine that the middle there is a triangle, the angles between each of these will be 120 degrees And that's the ideal angle between those central groups. Now remember there's that one 2p orbital left, so that's just going to go up and down, above and below the nucleus. And that's going to be 90 degrees from the central hybrid orbitals. So now each of the sp2 orbitals has an electron that's unpaired, so that could go on to bond with a hydrogen, another carbon, those could go on to form covalent bonds with other atoms. And our p orbital also has an unpaired electron, and we'll talk about what that will do in a second. Okay, so remember I mentioned that the sp2 hybrid orbitals will be kind of like in a triangle around the center of our atom. So let's pretend this is our center here. So we've got our sp2 hybrid orbitals in a triangle around that. And let's say that our carbon atom uses two of its sp2 hybrid orbitals to form bonds with hydrogens. So now we've got our unpaired electron from the sp2 orbital and an unpaired electron from hydrogen. And remember, they have to have opposite spin. So we'll just draw that up above too. Now let's say the last sp2 hybrid orbital ends up bonding with another carbon, which has its own set of sp2 hybrid orbitals. So in the middle there, between the two carbons, we get a single bond between those sp2 hybrid orbitals. We also call that a sigma bond. And let's see, so they've formed a single bond between them. Great. And the other carbon also has some hydrogens bonded to it with paired electrons now. Great. So those are covalent bonds. Now what about that p orbital we talked about? So remember there was a p orbital going above and below the carbon? Well, that had its own unpaired electron, right? The other carbon atom here also has a p orbital with its unpaired electron. And what's going to happen is these two p orbitals are going to team up with each other. And they're going to create what's called p overlap, or a double bond. And sometimes we call this a pi bond. So we've got sigma bonds, which are single bonds, pi bonds, which are double bonds. Now, this looks a little strange, right? Because we have p overlap above and below. So what's going on there? Well, that's just the nature of p orbitals when they form a bond with each other, because they have two lobes, right? They've got the upper lobe and the bottom lobe. So they actually create electron density above and below the plane of the bond. So it's just kind of weird, but we'll just go with it, right? Okay, so again, when we're looking at all these bonds, the angles between our carbon-hydrogen bonds will be 120 degrees. Okay. So let's just summarize everything we've talked about, and we'll kind of compare and contrast alkanes and alkenes, because we've definitely gone over a lot here. So let's just make a column for alkanes and a column for alkenes. All right, so let's list the orbitals for each. So we said that alkanes have 4 sp3 hybrid orbitals for carbon. And alkenes have 3 sp2 hybrid orbitals plus 1 p orbital, which is unhybridized for carbon. All right, so let's name the shape that we expect for each. So alkanes, we said, would form a tetrahedral shape or geometry. Alkenes are going to form what are called trigonal planar geometries. So trigonal tells us we have 3 things. Planar tells us they're all in the same plane. So we have kind of a triangle that's all in the same plane. And those would be our sp2 hybrid orbitals. Now let's talk about the angle that we expect between bonded atoms. So for alkanes with the tetrahedral geometry, we would expect an angle of 109.5 degrees. But for alkenes, because we have that trigonal planar triangular shape, the angle will be 120 degrees. Okay, so hopefully this table helps you kind of keep everything straight. I know it's a lot and it's all kind of abstract, so it can be hard to grasp initially. So don't worry if you're still a little confused. I remember this took me forever to understand or even wrap my head around. So initially I remember I just kind of memorized it, but eventually it clicked down the road. All right, so there is one other aspect of the geometry of alkenes that we need to talk about. So remember with alkanes, we said that cycloalkanes can't rotate their bonds because all of the carbon atoms are in a ring structure, so they're limited in how they can move. It's kind of the same with double bonds. Double bonds are really strong compared to single bonds. And if we go back to this crazy picture here, let me just make it a little less messy. Okay, so we said that we form these p overlaps above and below, and that's our double bond. In order to, let's say, flip one of the carbons, so let's say we wanted to kind of like flip it over, we would have to break these p overlap bonds. But they're really strong bonds compared to single bonds. So it would take a lot of energy to break that bond. So unfortunately, there isn't free rotation around a double bond. So there is no free rotation about a carbon-carbon double bond. So that means we end up with geometric isomerism. So this is similar to our cycloalkanes, where we said we could have 2 groups pointing up, so that would be cis, or one group's pointing up, one group is pointing down, that would be trans. So we actually get the same thing with alkenes. So we have cis isomers, where 2 similar or identical groups are on the same side of the double bond. And trans isomers have 2 similar or identical groups on opposite sides of the double bond. So down below we have 2-butene. So these are both 2-butene. And what I'm going to do is we're going to cut this alkene in half through the middle. So not vertical, but horizontal. So let's do that to the other one too. Okay, so on our molecule on the left, we have 2 methyl groups that are both on the same side if we cut the alkene in half horizontally. So that would be a cis isomer. Now, if we look at the other molecule, the methyl groups are on opposite sides. So this would be trans 2-butene. And again, we only consider the case where we're cutting it horizontally. This does not apply if we cut it vertically. That does not apply. It's only if we cut it horizontally, then we look at the groups and where they are relative to each other. So for instance, these two methyl groups have to be on different carbons. They can't be on the same carbon, if that makes sense. Now, you might be wondering, does it even matter where those methyl groups are? If they're on the same side or the opposite side, it still kind of looks the same, right? But these geometric isomers, cis and trans 2-butene, they do have different physical properties. So, for instance, down below, we can see in this table that cis 2-butene has a melting point of negative 139.9 and a boiling point of 3.7 degrees Celsius. Now, trans 2-butene, on the other hand, has a melting point of negative 105.6 and a boiling point of only 0.9 degrees Celsius. And you can even see that the densities are very slightly different as well. So these are different molecules, even though they kind of look the same. So it does matter whether those groups are on the same side or on opposite sides, which is why we do have to talk about geometric isomers. So if you told somebody, oh, can you go grab the 2-butene, then they should ask, well, cis or trans, because it does make a difference. All right, so next time we're going to start getting into physical properties of alkenes.